My name is Virginia. My call sign is NV5F. I have spoken to you guys briefly in show and tell and at other events about the AMSAT Cubesat Simulator. And I would like to do an expanded version of that this evening to explain what it is, what it's for, what it does, and how to build one. Over here to my right, there is a display of the demonstration of a CubeSat simulator, which I've constructed in operation. And I'll get to more of the details about that as we go. So here we go. Let me see if I can find the... Okay, CubeSats. So the first time I got exposed to CubeSats was in, I believe it was 2018 at Dayton Hamvention, and the AMSAT booth there was pretty big and cool. And I found this engineering model of a CubeSat, and I was amazed that something that small was actually a satellite. I was pretty enamored with that idea. This is what I'm holding in my hand is an engineering model of a 1U CubeSat. It's 10 by 10 by 10 centimeters. It weighs about 1 kilogram. So they're very, in relation to any other kind of satellites, they're very small. They're very inexpensive to build, and they can be added to rocket launches as kind of just supplements. They can be added to other payloads and sent up. They can be used for experimental, academic, and amateur radio purposes. And at this time, when I first saw this one, AMSAT had already put up several small CubeSats in the 2015 to 2019 era. The Fox 1A, which was AO85, Fox 1B, AO91, Fox 1D, AO92. Those three are all still up. They're all still operating in some sense. AO91 is, I think, the only one of those that still really functions as an FM satellite for AMSAT. Fox 1 Cliff was kind of a bust, AO95. We were all really looking forward to it, and they got it up there, and it stayed in safe mode. So they're still launching more. Other countries, AMSAT are putting up CubeSats. There are a lot of schools putting them up for experiments. They are low Earth orbit. They have magnetic attitude controls. They do tend to be doing natural deorbit over time because they're in such low Earth orbit. So they're small, they're kind of disposable. They're good for people who are learning about satellites, and they're great for amateur and experimental uses. Down here in the bottom left corner, that's one of my little alien entourage, also discovering the wonders of CubeSats. So that's CubeSats. This is the basic structure of a CubeSat right here. You'll see there is the top section there is going to be like the science payload section. So every CubeSat has some section of it that has sensors that are going to read data and telemetry or be running some kind of an experiment. There in the middle of the CubeSat, there's a battery section that holds the big batteries, and then at the bottom you're going to have the transmit and receive section, and then kind of in the middle under the batteries there's like a power handling section, and then the kind of the brain of the CubeSat is sort of between those that third tier up there. And then the little picture here at the bottom of the screen shows the CubeSat with its solar panels. And of course, that's what recharges the battery section here in the middle. And here's the diagram of how all that fits together. So it's pretty simple. It's like, hey, that's not any more complicated than like a radio that you can build at home, So these are really simple systems. That's the basic what's in a CubeSat. And the top 3 layers can have various different things of different complexity, but it's only 4 by 4 by 4 inches, basically. Very small little thing. This is the structure of a CubeSat simulator. It's a very similar idea. here at the top, we've got our payload board. This is going to have some kind of Arduino based thing, some sensors here. You can program this Arduino to do different things. There's a bunch of different pads here. You can set up experiments and make this payload board do different things. The middle board is the battery power. And then the bottom board is going to have the power handling and some voltage current sensors. And underneath on the very, very bottom is basically the brain that's over here in the diagram. That's going to be in this version of the CubeSat simulator. That's going to be a Raspberry Pi Zero W. So the transmit power on that Raspberry Pi is actually what's used as the transmit on this CubeSat simulator. Over here, my CubeSat simulator is transmitting telemetry. You can hear it on the HT that's over there, and you can actually see the telemetry on the little blocks on the software there, the Fox Telim software. And I've got one graph up there running of one of the solar panels. And that's why I've got the big light shining on the CubeSat is turning, and that's simulating sunlight, that big lamp shining on it. And you can actually see in the diagram the current and voltage changing on that particular solar panel on the graph there. And more about that software later in our broadcast. So this you can see here at the bottom shows the frame, the 3D printed frame of the CubeSat simulator. And you can see it next to the engineering model. It's basically the exact same size. It's much lighter. It's made of plastic and not a lot of heavy duty stuff in there. So it's not going to weigh 2.2 pounds like a normal 1U CubeSat. But it is the same shape and size of an actual CubeSat. So it basically is meant to simulate the size and the basic structure for various educational purposes. So here we are, the AMSAT education program. AMSAT VP, Alan Johnston, KU2Y. He's the VP of Education for CubeSat, and he came up with this based on a premise that was introduced a few years before that. In this AMSAT journal, which I did write the little article about my journey of building this, and they chose to put my funny picture of purple aliens on the front. And I was rather charmed and pleased by that, because I just sent them like a ton of pictures and they picked that one. I was really flattered. But in this AMSAT journal, there are many articles about the CubeSat simulator, including kind of some of the, and the history of it is also here on CubeSatSim.com. If you go to that website, there's a really good little archive of AMSAT journal articles, and you can read them all in order. And I actually did that because it's a good history of what's going on, how it was invented, what it's for. It is for educational uses, organizations and institutions who want to learn about building or launching a CubeSat. There's universities where they're like, hey, we want to do an experimental CubeSat. And they realized, AMSAT realized, hey, these people really need something to get their feet wet, to break the ice. You don't want to be learning while you're building the actual thing. So they're like, hey, here's a simulation you can build first. Science, engineering, and any kind of electronics students. Alan Johnston is an electrical engineering professor, and he has his students, his first year students, in their intro to EE classes. He teaches them how to solder. There's a lot of EE students who don't know how to build things, and he teaches them how to build things. And then as soon as he teaches them how to solder on one or two little projects, then he goes, okay, break up into groups. 4 groups are going to build a CubeSat simulator, and they spend their semester building these things. And so it's a very good a very good way to just learn electronics and kind of how sensors work and how soldering works and how power and battery charging and voltage converters. And it's really good just for that. It's good for STEM students, high school, elementary science classes. You can use the software to show kind of how current and voltage work. You can use it to just show kids how satellites, kind of how they tumble in orbit and how they, recharge when they're in the sun and use the batteries when they're in the shade and all that. It's useful on every different level. It can be used by individual hams like me who just are like, hey, I want to learn how this works. I want to learn how, and I want another project to build. I want to get better at building things. And this was not easy, and it was, but it was very fun and rewarding to see it work. And then, of course, you can use it for what we've used it for in AMSAT. You can take it to Moon Day or Hamfests and show it to people. And people get really excited when they see it. They're like, ooh, that's a satellite. Wow, I can't believe they're so small. And AMSAT does loan these out. You can actually contact them and borrow one for a class demonstration or a scouting event or a Hamfest or anything where you're educating people about STEM. So, or satellites. So that's kind of the purposes of this, at the root of why this was even done. So these are the systems on a CubeSat simulator. It does have the 3 boards. I've discussed this already. Over there to the left is the Raspberry Pi. That's the brain, and that's on the very bottom. The bottom board is going to be the voltage and current sensors for all the solar panels and for the battery and for the recharging circuit. So there's 8 of those sensors on that bottom board. So that bottom board is basically the brain and the power system. The middle board is super simple. It's the batteries, just 3 batteries. And then the top board is the payload. So first we'll talk about the Pi Zero. It's got a little 16 megabyte card. That card has programming. You can download the programming from AMSAT, and that card basically turns the Raspberry Pi into a CubeSat simulator. It's all coded with all the stuff you need. You can tell it your call sign, and when it fires up, it'll send your call sign. It will transmit. It transmits on 434.9 megahertz, and it will transmit APRS. It'll transmit frequency shifted keying data telemetry. That's what it's transmitting right now. That always runs on our FM, on the AMSAT FM satellites, the CubeSats. That runs, and you can actually receive telemetry for any satellite that's operating, that's coming over. It should be in that mode. Even it's called data under voice, and it'll actually transmit. That's what DUV is for. That'll transmit while people are actually using the satellite as a repeater, so people can receive telemetry on these and use that software that I'm using over there for my simulator. It will transmit SSTV, and if you see there on the right, the picture shows the little Raspberry Pi camera there. And if I put it in SSTV mode, it'll take a picture every couple minutes, and it'll transmit a TV picture. And it will also transmit telemetry in CW. So it's got one other mode. It's some kind of packet mode, and I'll admit that I have not done enough research on that to know what it is or put it in here. So my apologies for that lack of information on the 5th mode. So that's the brain and all that. That's what the Pi is doing. When you get to the power is nothing but 3 AA 1.2 volt nickel metal hydride batteries. It's got the battery charger circuit, and it's got a boost regulator, because 1.2 times 3, that's 3.6. And if you really charge it, it'll get up to about 3.8 or 3.9. And that doesn't quite cut it. So we got to boost that up to 5 volts to power the Raspberry Pi. And the solar cells, 5.5 volts on each cell. You'll see the different cells. You'll have 4 of the larger cells, 2 slightly smaller ones because we need them to accommodate the antenna sticking up off the top, and then the charging stuff on the side of one of the things. And then if you have the Pi cam, you'll use 2 smaller solar panels on that side for the side with the Raspberry Pi camera, which is an option. You don't have to put the camera in. And then the sensors, I got 2 different sensors here. The little purple sensors for voltage and current are the ones that are recommended, but they got, as a lot of things did when we were building this, those sensors got really hard to find and really expensive all of a sudden. A couple years ago, everything, electronics, it was, it's like we went back about 30 years in time and things got really expensive and really hard to find. So you can use the blue sensor there on the right. It's also an INA 219 sensor, and it's a little bit bigger, and you have to kind of fiddle things. And you'll see there on the bottom left, I've got the big blue sensors in there, and they were more plentiful and seem to have a little better quality controls. So I use them, and you have to just be a little bit creative about getting them to fit on the board, but they work okay. And then, all that with that's basically our power system for this CubeSat simulator. The next system we'll talk about is the payload and their other peripheral, like the Pi camera. The payload is a Arduino based board. I used the SparkFun board. You can also use the Blue Pill board, STM32 Blue Pill board. They're both programmable through the Arduino interface on a PC. In addition, on the payload board, we have the 2 sensors. We've got the 9-axis motion sensor, and then the one that senses altitude and barometric pressure, temperature. It's kind of the weather station on board the CubeSat Sim. Those 2 sensors are basically sending telemetry, which will be received by the software over there. Is actually a little box there that's showing those, and I'll talk about that in a minute. And then the Pi camera for slow scan TV. And then, of course, we've got our little 440 megahertz transmit antenna. This does not receive. It is a transmit only. One of the things I thought to maybe try to do with it is eventually figure out how to get a transceiver kind of thing, a receive transmit kind of thing put on this thing. So that's kind of one of my personal thoughts for pushing the CubeSat Sim further, as I get more accustomed to how it works and learn more about it. All right, so then you've got your cool CubeSat simulator, and you've got everything running, but you need to be able to know how it's doing. So you've also got to set up a ground station for it. Here on the left is what is typically used is an RTL SDR. That's this little inexpensive software defined radio that you can plug into a Pi or a PC. And I chose the PC route simply because I have a PC and I didn't want to have to buy a Pi 4 and a display for it or an adapter for it or any of that. So I just used my computer. I also happen to also have an RTL SDR. So that closed the deal for me. I was like, well, I'll just plug this into my computer. So that's what you see there on the bottom right is my little system there on my laptop. It's sitting right there. This is the Fox Telem software, which can be obtained free from from AMSAT, and it is made specifically to receive telemetry from the Fox CubeSats. And there on the bottom right-hand corner is the software itself, and you'll see here, this is the signal. That's the FSK data signal sending telemetry. This is called an eye diagram. This basically just shows you've got a good solid signal, and it'll open up and make this kind of elliptical shape showing the average top wave, the average bottom, lowest voltage, and then, you know, it'll open up and show that you've got a really solid signal there. And then here's the signal here, the peak of that signal. This is the diagram. This is the little table showing all of the information coming from the one of the sensor cards with all the temperature, altitude, humidity, pressure, all that. That's the sensor there. And then these are like the this is the battery and power system sensors here showing what voltages you have. And then this is a couple of the solar panels right there that the software is decoding from the signal. So that's what the ground station is for. You got to have that to kind of know how so to be able to just demonstrate that it's acting like a satellite. And this is further showing the diagram of the solar panels. You can tell it to show graphs of what these little boxes down here, or these 6 boxes at the bottom. You can tell it to show graphs of several of these at once to compare them, or just one of them. It's a little easier to see when you're showing one. This is the voltage on that particular solar panel, and this orange guy here is going to be the current on that solar panel. So you can look at each different signal in relation to other signals if you want to with the software. It's pretty neat, and it just helps you better understand kind of what's going on with the power, the batteries. It really is great when you get it sitting in sunlight, because when it's sitting in sunlight, it will actually charge the batteries. It'll really does kind of act like a little satellite. So what if you wanted to build a CubeSat sim? So this is not a kit. I'll tell everybody right up front, it's not a kit. You have to source your own parts. The thing you can get from AMSAT, which is very handy, is that you can get the circuit boards from them. They're about $35. The great thing about getting it from them is that it does have a bandpass filter on it that's made out of tiny little surface mount parts. And if you get it from AMSAT, the surface mount parts, they had the board house put them on there for the bandpass filter, which is great. If you source the boards yourself, because they do have the Gerber files for the circuit boards, if you source them yourself, you can probably have the board house do the same thing, put the bandpass filter on there for you. That's the one thing that I bought. I was like, okay, I've got these boards, you know, I'm all excited now. And then you go to this site called GitHub, which is a open source project sharing site. There can also be little private groups on here, but there are lots of public projects. And AMSAT Cubesat Simulator is an open source project. And on this is the files for everything from the 3D printable frame to the circuit boards. But then you also have this wonderful bill of materials right here, and it's long and it's detailed, and it's not nearly what, you know, something would be on a, you know, majorly huge piece of equipment, but it makes you realize how many parts are in something that small. So it's a challenge, because you have to learn how to, I had to learn how to not be scared when I got on DigiKey and go, oh my God, there's like 7 million parts. What do I get? It's a very good education in what it really is to, you know, like figure out as someone who's designing something or prototyping it, like, where do I get parts? And he has you know, they have links for all the parts on here, and you go to a link and it would be like, this is no longer available. Well, then you have to go find it somewhere. And that's what I had happen with the little skinny solar panels for the camera side. I had to go, gosh, Amazon doesn't, or whoever, I think it was AliExpress or somewhere, doesn't have these anymore. They just weren't available. And so I got on Amazon and I had to find something similar. You know, I was like, well, these are the same, about the same size, almost the same, you know, almost the same exact power, you know, the configuration on the contacts on the back's a little different. I can make it work. So it's good. It's a good challenge. It makes you kind of be resourceful and figure out how to get things to work. And I had to do that quite a few times. And the instructions are also on here. There's a great, very detailed set of instructions with exhaustive photographs of how to build everything in like copious numbers of steps. And even as good as the instructions are, there were things I was like, they kind of left something out there. I'd have to go, you know, I have to write someone an email or get on the discussion board. They've got a discussion board on here. I'd have to get on there and ask somebody something, or just figure out what, like the little bitty bushings and the little tiny screws to put the Pi camera on were not listed in the BOM. And I was like, okay, I have to figure out what these things are, and then I have to go find some, you know. And that was the very last step. And I was like this close to getting it finished. And I couldn't finish it because I had to get on Amazon and find these things and then wait 3 days to get them. And, you know, it's like, so it's kind of a cool project, but it don't expect to get it done in a few days. It took me several months to get this done. I really started it in the summer of 2021, you know, getting materials. And then I kind of got bogged down in some of the computery stuff, which is the part I'm least good at, like all the, you know, getting the Raspberry Pi to work and all that. And then last spring I started like, okay, I'm going to do this. And then by the end of the summer, last summer, I finally had it done. So it took me a little over a year. And granted, I wasn't working that whole time, but you know, it took me a while. So, but I've done it. Jack is about to do it. He wants to build one. He's got a lot of the parts now. I helped him with, I had a lot of leftovers. The great thing about it is if you want to build it with a friend, you can share expenses, because it's hard to buy just 1 or 2 of certain parts. Sometimes you have to buy 20 of something and you only need 3, you know. So it's a great way to reduce the expenses if you share them with somebody else. So it's kind of a good fun friend, you know, drafting along with somebody project. And I've done it, and I can definitely run interference for anybody else who wants to do it, because I have, if you read my article that's in the newsletter this month, it's republished from the AMSAT journal, and it talks about a lot of the mess ups I had. Okay, and if you want to build one of these, a note about the Raspberry Pi Zero, they're hard to find, and when you do find them, look how much they are. They went from about $8 to about $99 in less than a year. I don't know what they cost now. This presentation was put together last fall. The designers of this, Alan Johnston and company, are coming up with an alternative version of a CubeSat simulator that runs on a Pi Pico. That's this little guy here on the right. They're still pretty plentiful and much less expensive. We've been hoping, you know, I'm not sure how supplies are for Pi Zero, but you know, they were saying that at the beginning of this year that they were supposed to start costing less and being more plentiful. I have not checked on that, but so if you want to build a CubeSat simulator, it might be good to wait a little while for the next version to come out, because it's gonna be based around the Pi Pico. And I actually bought a Pi Pico, kind of anticipating maybe, you know, having another go at this from another perspective. So
Pico's running $6 on the work.
Yeah, and they're not very expensive, and they'll vary in cost based on whether or not you get the header pins with them or whether or not they have Wi-Fi. But the basic Pi Pico is yes, much less expensive and more plentiful. So all right, so I have a little channel that I have been making little videos about the CubeSat simulator on on YouTube. It's called Satellite Lily, named after my little funny alien girl there. And so, you know, join AMSAT, join the CubeSat Simulator project. You don't have to build one. You can just be a supporter of it by getting the word out or borrowing one for a school, school thing. Kathleen, you might want to, use this for school for something.
I can actually write a grant for stuff.
Yeah, you could write a grant to probably get all the stuff and build one. Join the discussion on GitHub. There's a discussion board there, and it's quiet a lot of the time. And sometimes I'll just go on there and answer people's posts just to get people talking again. Build or borrow a CubeSat simulator, and join me on my little YouTube channel. I haven't done much recently, but I think I'll be doing more in the very near future. So, but there are some little videos about the CubeSat simulator, just trying to kind of get the word out on it. So, anyway, are there any questions?
So the satellites, are they geosynchronous?
They are not. They're low Earth orbit, which means they're basically up around 220 to 250 miles up, and they orbit about every 90 minutes. So when one of our FM satellites goes around and we work a satellite pass, we get about 10 to 12 minutes of that satellite going over when we can work it. Anybody else?
So I gather you have to program it through Wi-Fi. Is that?
Well, when I was building mine, I basically just used the Arduino interface to upload a program that basically runs the sensors on the payload board. If you're programming it, if you're wanting to write new code for it, you would just do it through a USB interface between the computer and the Arduino. If you want to do programming on the Pi, you can do a similar thing on the Raspberry Pi.
How hard is the programming?
I'm not very into coding, but I've done a little bit of Arduino coding, and it's pretty easy, and there's lots of great resources on learning it. And coding is one of my weakest areas, so I'm actually doing a little self-study course that involves some Arduino coding, so that I won't, be completely lost in the rest of the 21st century. Anybody else?
Do you ever see this replacing like drones and stuff? Because the drones are being used more and more in different areas.
No, this is very different than drones. Satellites are way up in orbit. And what I'm showing here is just a simulation of a very small 1-unit CubeSat. So drones and balloons and that kind of thing are, drones can only go so high, balloons can go really high, and then satellites are just way up there. They're doing experiments from low Earth orbit. So there's really not any like super intense crossover between the two. They're very different things.
Can you say that it maintains attitude control via a magnet?
They do have, some of the CubeSats have an attitude control based on, I don't know a whole lot about it, but it's a gyro based on, magnetism, probably Earth's magnetic fields and stuff. I don't know a whole lot about how it works. It's one of my areas I need to look into.
And I just looked up the 02 is running $26, and the software on the GitHub site looks with it.
Okay, that's good. Like Pi 02.
Yeah, Pi 02.
Okay, very good. That's good news for us. Anybody else?
What's the life expectancy once they get it launched?
A little CubeSat like this. Well, a couple, like the AO85 worked for a couple of years. AO91 the same, or AO92 the same. AO91 is still working, and it was put up in like 2018, I think. So the main thing of life expectancy has to do with how well the batteries can still just maintain a charge. When satellites get to be a few years old, they'll basically say, you know, try to only use certain ones during daylight hours, you know, when they're basically being powered by the sun. So it's hard to tell. Sometimes the satellite AO7, which is the 7th amateur radio satellite that was put up like forever ago, is still operating. And then there's some that we put up that, you know, don't even manage to turn on. But it's, you know, we usually expect a couple years out of something, and sometimes even just a few months. And sometimes things are designed to deorbit very quickly, and are only just meant to be experiments for a little while. So it varies, but we kind of think of them as, if it lasts more than a couple of years, we're like, yay.
It is possible to get them to other orbits, but they're usually more robust CubeSats that are more like a cubic foot.
Yeah, ones
And-
that have a mini
And
units.
then you can get them up, all the new space companies are coming up with small sat capability for launch. SpaceX sends transporter missions, which is, I think the last was in January, and sent 114 satellites in one blast there. But another way to get them into space is also to send them on a Dragon, and they can be released from the space station.
Yeah, they just have this little thing that they drop satellites out of on the space station. It's pretty cool.
Maps, if you can-
Yeah, the small sats, which are, you know, bigger than CubeSats, but not by a whole lot. That's kind of the thing, is everything's getting smaller, and we can, but the thing is that FCC now has a thing where if you put a satellite up, you have to show that you can deorbit it within 5 years of its last usefulness. And that's making us go, okay, we've got to figure out deorbit strategies, whether we have big, like, you know, there's one idea of turning the solar panels, make them break away and turn into kind of a sail that will cause drag in the upper atmosphere and deorbit satellites. That way you could use compressed nitrogen as propellant to deorbit them. A lot of them will just deorbit on their own, you know, within that time, just because they are so low in the, you know, so low in orbit. So, yeah, there's a lot of cool stuff happening with satellites right now, and a lot of astronomers that are a little bit freaked out by that because it's messing them up. So,
Mainly they shortcut Starlink.
yeah, the Starlink and the Kuiper satellites are like really kind of getting astronomers a little bit concerned. So.
What kind of money do you have invested in this CubeSat?
This one is probably about, if I were to say exact number of like the parts that are actually used in it, it's probably a couple $100 worth of stuff. But if it's what you actually have to spend, it's probably more like $400 because of all the extra stuff you end up having to buy and things that don't work and things that, you know, it's a few $100s, but it's really an investment in, you know, your own education at the same time. It's a really neat way to learn just the basics of how satellites work. I feel a lot more certain of what's going on in a satellite now.
So these are all meant to have a orbit that decays and then burn up in the atmosphere.
Yeah, pretty much. Yeah, they're pretty much meant to be disposable. They're not meant to last terribly long. Yeah, we're definitely not thinking we're ever going to see these again when we put them up. So yeah, in microscopic atomic sized pieces. Yeah. Yeah, exactly. Yeah.
The simulator is transmitting to the handy-talkie.
Yes, the simulator is just transmitting on 434.9, and the handy-talkie is just set up on that frequency. And then the RTL-SDR is also set up to receive on that frequency. It's transmitting at such a small power level, like a few milliwatts, I think, so that even I think even like non-hams can, legally use it because it's not transmitting at any appreciable level. So just across the table, basically.
And I'm assuming your temperature and humidity sensors and all that were done just for demoing that it can sense something and send it, since
Yes.
humidity in space is.
Yes,
pretty
there's,
low.
humidity is, we're not gonna have humidity or atmospheric pressure or, yeah, exactly. So that sensor on there is to just show, here's what you do with the payload board. You can put sensors on it and program this Arduino to relay that information, and to the Raspberry Pi to be transmitted. So,
To send, you can use those sensors now better because you're not gonna send it into space.
yeah, exactly. So you can just enjoy the sensors there on the Fox to Limb. So yeah, it's not practical. It's not space worthy. When I first posted videos of it on YouTube, there's always these really pedantic people who come on there and go, well, that's just resin printed frame and cheap solar panels. That's not space worthy. And I'm like, simulators right there in the name. Smarty pants.
Yes,
Yeah. Yeah.
you said it took you over a year or right in to build it, that you didn't work on every.
No. I say on again, off again, and more off than on. So, I went in spurts. I would work on it for a little bit, and then I have a really downtime of, being busy with other things. And then starting in about April or May of last year, I was like, okay, I'm really going to do this. And by the end of July, I finally did have it finished.
So would you guesstimate how many hours you put into it?
Oh gosh, I couldn't say. I really don't know. But for me, it would be more hours than for some other people, because some other people are just better and quicker at building than I am. And I made a lot of mistakes and I had to redo some stuff. So, and there were frustrating, very, kind of moments where I was like, I can't do this. I mean, there were moments when I thought I was just never going to finish it. So.
Oh, and I'd also like to point out, besides having space for these satellites that are more expensive, the really expensive part is getting into the orbit.
Yes, that's much more expensive than building.
You went from $100,000.
Yeah, building a CubeSat probably costs, but about $8,000 to $10,000. I don't know. I'm just guessing. It costs $100,000 to put one in orbit. So,
Okay.
because
and
it's all by weight.
Are there any ground-based or planet-based or stays on planet applications for a satellite?
Well, the CubeSats that are up in orbit now, we use them as repeaters. So if one is going over and I put my call sign in, and it gets to the satellite, then anybody in the footprint of that satellite who's got the right antenna, and it's just 2 meter 440. All you have to operate satellites is a technician class license. And so for us as amateurs, it's a way of communication to just challenge us to learn how to track satellites, but we can use them for communication. And then of course they do transmit telemetry. We can receive that telemetry and use that Fox to Limb software that I have right there to actually get the telemetry from a satellite in space. So you can check on the health of the satellite. And
I guess if it'll work in space, it'll for sure work on the ground.
Sure. I mean, they have to test them on the ground before they put them in space.
So we stick it in the wood somewhere now.
Yeah. So these.
I did see a tweet that the repeater on the ISS has been turned back on.
Oh, very good. I know it was kind of off for a while for whatever reason.
Today.
Awesome. To try to get on this weekend. Anyway, I appreciate everybody's attention, and let me stop the recording. If I can get that to. Okay.